We are going to expand our horizons a little bit today and think about something more complex than a tree and not just focused on fast search, though there will be some search, because I'm a search kind of person. We'll talk about graphs. So they help us to answer this question of how we can represent constraints or more complex relationships, like movement between locations, such as cars on roads where they have speed limits or they have a time that it might take to travel that road, and we need to make some decisions about which roads to take on a trip or things like that. Airplane flights between airports, possibly with costs associated with each of those flights. Packets in a network they have to navigate. And so knowing those connections and those constraints, where can you get from one place to another? And ordering between items in a schedule, such as courses that have prerequisites, or a startup sequence where some process depends on the work of another being done. Things like map coloring, if you're laying out things and you want them to each have their own unique color or their own unique feature of some kind, then we can use graphs for that. So we'll talk about the graph abstract data type, and then we'll get into some of the representations and a little bit of problems with them. To define, a graph G is composed of vertices, or nodes, if we think more in the tree-like language. I like to call them nodes as well, but a mathematical setting or a more theoretical setting will typically call them vertices. And then edges, or arcs, connecting those vertices, or those nodes. So there will be some connections between them, possibly, and they will not all necessarily be directly or even indirectly connected to each other, but we'll be able to see what those connections look like by examining the edges and doing some work to see which nodes, which vertices they connect to. We write that G equals V comma E to describe the graph, and then we could list out all of the vertices and we could list out all of the edges, and it would give us the same information as, for instance, this visual graph over here. The vertices from the set V are usually denoted by lowercase letters like U, V, and W, and edges often use E's, lowercase e's, to represent an individual edge from the set, capital E. And it will be a pair of vertices, such as U, comma, V, or in our visual graph, A, comma, D is an edge that's in here. And those, of course, have to be vertices from our set V that's a part of our graph. And then basic graph operations, we often want to insert or remove edges. Sometimes we insert or remove vertices, and we may query if two nodes are connected or of various relationships that those nodes might have to each other. We call two nodes adjacent if they are joined directly by an edge. The degree of a node is how many edges that involve that node. And we'll use DEG as if it were a function to talk about the degree of a particular vertex or a particular node. And a path between two nodes U and V is a sequence of edges that you could follow beginning at A and ending at V. Sometimes there will be no path between two particular nodes, but if a path exists, then we'll get a sequence of edges that start us at our starting point, U, and end us at our ending point, V. The number of edges on a path is its length, and a simple path doesn't cross through the same vertex twice. So there may be cases where, for instance, if we were trying to get to C, we might take a wrong turn, go through B, and have to loop back through A and get to C, but that's not a simple path. A simple path would be the direct one. And a cycle is what I just showed a moment ago, where you pass through the same node twice. So in other words, a simple path contains no cycles. A cycle is a repeated loop where we go through the same place twice, and we typically want to avoid those. In fact, there are many algorithms that are designed specifically to remove cycles from graphs so that we don't have to deal with them. A connected graph means there exists a path between every pair of nodes, and a complete graph is when there exists an edge between each pair of nodes. All nodes are adjacent, not indirectly connected, like A and G are in this graph shown here, but directly connected like A and C or A and B are. So a complete graph has many, many edges if it has more than even a couple of vertices. And a connected graph is more like the one that we've shown here, where you can always get there from here. It just may take a few steps to get there. A directed graph is a more specific type of graph where the edges have a specific direction to them. The one displayed up here is an undirected graph because we have no indication of whether it's one way. So one-way roads provide us a good example of where a directed graph is needed versus two-way roads, highways, things like that. We can get from A to D and we can get from D to A without any complication. So a directed graph, edges have a specific direction to them. So an edge like AD means that from vertex A you can get to D, but unless you see the reverse edge listed, DA, then you may not be able to get from D to A. This is also useful when you're tracking states of things. If I eat the cake, I can't go back to the state where I have the cake. I hope. Don't try it. It would be gross. And a weighted graph is a graph where edges are associated with some weight or some cost. And these are often done in problems where we have some actual feature we're trying to minimize or maximize, such as travel time. We would attach the travel time of each of the roads to the edges that represent those roads, and then we would be able to choose the fastest trip to get from one place to another. A simple graph is undirected, may be connected or unconnected, meaning that there may be some nodes that aren't connected to others. There are no self-loops. That's not cycles. That is edges where the same vertex starts and ends it. So there certainly are some types of graphs in which I could take an action from A that leads me right back to A. But a simple graph doesn't contain those kinds of self-loops in them, and therefore we don't have to try to avoid them. And there are no duplicate edges, no multiple edges. We don't have to repeat that A is connected to D and A is connected to D. So we can achieve many of these features of a simple graph, even from a non-simple graph, by doing things like removing self-loops, finding them and removing them, or removing any duplicate edges as well. So one good question is how many edges a connected graph has. A sparse graph has O of the cardinality of V. That's what these bars here mean. They don't mean absolute value when you're talking about a set. They mean the size of the set, the cardinality. So a sparse graph will have edges that are on the order of the size of V. A dense graph has on the order of the size of V squared edges, meaning that if lots of the edges are connected to each other, and in fact if all of the edges are connected to each other, then we're going to be in this size of V, cardinality of V squared situation there. And these are just definitions of sparse and dense. These are not proofs that certain types of graph have one of these or another. We could certainly do some math and some proofs around those. But let's talk about representation of graphs. We can represent graphs with a list or with a matrix, among other possible representations. So we could keep an adjacency list. For every node, we could maintain a set of adjacent nodes, saying which nodes is it connected to. So in the example I have here, 0, 1, 2, and 3 are all connected to each other. And so the list for 0 would contain 1, 2, and 3. The list for 1 would contain 0, 2, and 3. 2 would contain 0, 1, and 3. And 3 would contain 0, 1, and 2. And that shows us all edges, and through each row shows us all vertices. This graph here is not quite so fully connected and is directed. So we need to know when we're making this kind of list whether it is a directed or undirected graph. You notice the first one was undirected. Our list for the directed or undirected graph may appear the same, but when we deal with it in code, we need something to indicate to us whether those edges are directed or not. Okay, so 0 connects to 1, and 1 connects to 0 and 2. 2 did not, by the way, connect to anyone. So that's how we can indicate that the direction was from 1 to 2, is that 1 connected to 2, but since 2 has no edges out, then 2 connects to no one. Here's a larger example of an adjacency list. This is not a connected graph in that there's a little cluster of 0, 1, 2, 3, and another little cluster of 4, 5, 6, 7, but these two clusters are not in any way connected to each other. So if someone asked me to find the route from 0 to 7, I wouldn't be able to. And that's going to be apparent in the adjacency list here because the top numbers will only contain the top numbers as who they are connected to, and likewise the bottom numbers will only contain the bottom numbers. So we can see that 0 is connected to 1 and 2, and so on for 1, 2, 3. They're connected to each other, not as fully connected as the previous example. And then 4, 5, 6, 7. 4 connects to 5. 5 connects to both 4 and 6, and so on through here. Instead of a list, we could also use a matrix, which will indicate to us the connectivity between particular vertices in sort of a table or matrix format. We create a table or a matrix of cardinality of V by cardinality of V, size of V by size of V. So in this example, I have 4 nodes, so it will be a 4 by 4 matrix. And here's our matrix. You can see that row 0 contains all of the indications for whether 0 is connected to something. 0 is not connected to itself. 0 is connected to 1, 2, and 3. 1 is connected to everyone but 1 itself, and so on. In an undirected graph, the matrix will always be symmetric like this, where if one thing is connected to another, then that other thing is connected to the first. If 0 is connected to 1, then 1 is connected to 0. In my other example, we have where this indicates that 0 is connected only to 1. It's not connected to 0 or to 2. And 1 is connected to both 0 and 2. And 2 is connected to no one. So the 0 or the 1 indicates true or false. Is there a connection there? And we can lay these out to be a little more human readable if we'd like to as well. We could write the 0, 1, and 2, and that clarifies a little more for the human reading it. Here's a larger adjacency matrix, but we can do interesting math and interesting computing tasks with these matrices, as well as them being a useful reference for a person looking at them too. So this is an undirected graph. You can see even though it's not every node connected to every other node like before, it is still symmetric. There's a 1 on this side of the center line here, and so there's a 1 on that side of it, and so on all through here. Now thinking about which of these we would prefer, will require some thinking about the structures that they represent and the tasks that we might need to use them for, and of course things like memory used as well. So for example, the space required for an adjacency list is typically much smaller. Unless every node is connected to every other node, then we're going to be a pretty reasonable representation. We'll have the n to represent a row for each node, and then m will be the edges. We have to store the representations of each edge. Whereas an adjacency matrix, of course, because it's size of vertices by size of vertices, it will be n squared for n vertices. If the maximum degree, meaning the most connected node, is the value d, and we know that d is less than or equal to n because that node can only be connected to up to n vertices, then checking if there's an edge between two things requires looking at the row for u, the starting point of that edge, and searching through its row that may be of length up to d, the maximum degree in our graph, and finding whether that vertex v is represented in its list there, versus an adjacency matrix where we just put the index for u and the index for v, and we get it in O of 1 time. To insert a vertex is very simple. It's O of 1. We can just put it on at the start of the list, the start of the row for a particular vertex v. To inserting a vertex would require adding a new row with nothing in it. Inserting an edge would require adding that edge to the row for whichever vertex it represents. Versus in an adjacency matrix, adding a vertex is complicated because we have to resize our matrix. And so that's going to be O of n squared to resize the matrix and to copy overall values and add new values for that newly added vertex. Inserting an edge in an adjacency matrix is as simple as flipping a 1 to a 0, or 0 to a 1 rather. Removing a vertex is the opposite. Removing an edge is the opposite. We will just flip the 1 to a 0 in the adjacency matrix. In the adjacency list, we can remove the edge by finding it in the list and removing it there. Removing a vertex could require removing all of the edges for that vertex, meaning all of the places that it's found in those lists and removing it there. And in an adjacency matrix, again, similarly, we are resizing, so it could be O of n squared. So there are ups and downs to both of those. It depends on what your most common uses are. If it's quick lookup and you don't care about size, the matrix can be very useful. If you're changing and adding vertices often, then the list might be most useful. And if you have limited size, the list might be most useful. Let's look at our first actual problem of using a graph to solve something. We want to find the shortest path. So given a graph G, we want to ask questions like, what's the shortest path from some starting node U to some end node V, such as going from A to G in this graph, or things like that. So the example we'll step through is going from A to H, which is a little bit out here, so we'll have to do a little bit of work for it. And similarly, finding a path from A to G, like I mentioned, could be a simpler one. We'll see. So, and if there was a disconnected node like K, we also want to be able to say there is no path to that one. So we want it to be complete enough that we can tell if we didn't find a path, that indicates there actually is no path. If we think about this with a data structure that we do know, because a tree is just a less connected graph, then we can think about two different search approaches, two different approaches for finding shortest paths in that tree. One is depth-first search, where we check children, children, children all the way down some direction, and then we start to look back at the places that we've been to if we didn't find it. And there's also breadth first search, where we check all of the first depth level of data, or depth level 0 at the root. Then we check depth level 1, then we check depth level 2, and then we check depth level 3. So we're slower at diving into depth in breadth first search. We are quicker at diving into depth in depth first search, and we are slower to finish up a particular depth level, like depth level 2 up here will take us a while before we get back up. I'm sorry, depth level 1 will take us a while before we get back up here. Because a tree is a directed graph with no cycles, meaning that you can't loop back to the root or things like that, and it has a directed path from the root to every node. So coming back to graph territory, if we take the input of some starting vertex and an ending vertex, we can try a depth first traversal, much like the depth first example we saw in the tree. The output for that algorithm would be whether or not a path exists between that starting vertex and the ending vertex. We also could make the output be the actual path. That would require tracking a little more. And so for now, we're just going to indicate whether there's a path, and then you can work on algorithms that actually track what that path is. We mark all vertices with some Boolean to indicate that we have not visited them. So we might keep a table, for instance, of all of the vertices and say, have we visited that vertex? No, we have not right now. And then we're going to start. So we mark the starting vertex as visited, and we push it onto a stack. And then we have a relatively simple procedure. While the stack's not empty and the top of our stack is not our end vertex, then we'll pop off of the stack, and for each adjacent vertex A from that new vertex that we popped off of the stack, V, we will see if it's visited, mark it visited, and then push it onto the stack. If we do not mark things as visited, we end up with endless cycles, potentially, where we go A, B, G, F, D, A, B, G, F, D, A, B, G, F, D. And so this marking as visited helps us to prevent that, because when we came back around and saw A again, we would realize, oh, I should try a different route. And so if we continue that loop until either the stack is empty or the top of the stack is our end vertex, then when the stack has finished, we can see either we had the end vertex as the top of our stack, and that's what caused us to finish, or nothing was left on the stack and we explored everything we could get to from our start vertex, and that means that there is no path. So if we found the end vertex as the top of our stack, great, we return true because a path does exist. Otherwise, we return false because a path does not exist. Like if we're trying to get to K from anywhere else, we could explore all of the connected part of the graph, and then we would find that K never came up in it. Our stack got empty, and we never reached K. A breadth-first traversal is the exact same design, except instead of using a stack, we use a queue. So the stack will cause us to think more sort of immediately of, I want these things that I just saw. That looks good. I just saw it. Great, I'm going to go that way. Whereas the queue will cause us to sort of put off some work for a while and let us sort of wait to get back to those nodes. When we expand A, for example, we'll put all of its children, all of the vertices that we found that were connected to it, onto the queue, and we'll actually put those at the front of the queue, and they will get handled before any of their children, before any of the vertices that they are connected to. So we'll see some examples of those. The difference between depth first search and breadth first search, therefore, is this stack versus queue ordering. Depth first search looks at effects deep further out into the future. It sort of says, okay, but what could happen next? What could happen next? What could happen next? whereas breadth first search looks for things that are nearer to the current. Some people frame this as instant gratification. I almost sort of see it as a patience. You're patiently checking what's nearby before you run 100 miles away and realize that you actually left whatever you're looking for at home. So there's some variation on perspective of that. There are modifications needed to produce an actual path. You would have to track the path along the way with those vertices that you're putting in to the stack or the queue. If there is less than or equal to one path, then depth first search and breadth first search return the same answer. Meaning if there's only one path, of course, they're both going to find that path. And if there's no path, they'll both discover that there is no path. If there's more than one path, breadth first search will return the shortest path. So it does have some benefits in that way. Again, it skips the I drive 100 miles to buy a new one because I didn't thoroughly check around my house kind of problem. So some examples of these. If we assume that when we see the nodes that we have edges to, they're inserted in alphabetic order, then the nodes that get visited on the way of going from A to H, depth first search will visit A. It will see that A has children B, C, and D, and they'll get put on the stack in that order, meaning B will get buried by C, and C will get buried by D. So when we pop, D is what will come off. Then F will go on, E will go on, and then F will go on. So F will be on top, and F will be what we pop. G will go on, and H will go on. So H will be on top, and H will be what we pop, and we get a solution relatively quickly that way. Not always true. If, for example, D had been over here, or over here, we might have had to try some dead ends in there and kind of pop our way back to one of these nodes that's closer to A. Versus breadth first search, it will visit more things in this example, but it will find an equally good path. So it will check A, B, C, and D because it's putting them in a queue. So B becomes the front of the queue, C becomes second in the queue, D becomes third. And when we see the children, they won't change the ordering of B, C, and D like would happen in a stack. So once we've explored B, C, and D, then we will try the things we've seen after then, G, E, F, and H. And the final path will be the same. But for something like A through G, trying to get from A to G, depth first search will suffer a little bit because of the fact that it's sort of quickly trying to dive down pathways. It dives down the D pathway and stays committed to it for a while. So it dives down D. It then puts E and F onto the stack, and then it puts H and G onto the stack. So it dives down the H pathway before getting to G finally. It's got to get H out of the way, notice that that was a dead end, and then pop off G and be able to explore that way. Whereas breadth first search does the same amount of work and finds a shorter path in this case. Breadth first search will tend to do more total work if there are easy paths that depth first search can dive straight to, but it will always find the shortest path. So here it explores A, B, C, and D, and in the way of exploring B, C, and D, it would have put G onto the queue. When it explored B, it would see that B had an edge to G, and it would put that on the queue, say, I'll save that for later. Right now I'm checking the depth level 1 nodes. And then it explores G, and it finds that the shortest path is from A to B to G. Both of them would visit all connected nodes to try to find a path to K. They would visit them in a different order, but they would visit all of the nodes and eventually conclude that false, there was no path, or null if you were asking to return a path or that kind of thing. So graphs are useful in representing and solving many constraint or relationship-based problems. The graph abstract data type can be represented using lists like the adjacency list, which can be good for graphs that have to change a lot, adding vertices in particular. And you can also represent with an adjacency matrix, which is very helpful when you have a graph that's relatively stable. Things are going to be there and not add too many vertices or remove too many vertices too often. We've got a good amount of terminology around graphs, which are actually important both now and into the future of other algorithms you'll learn, and so you should be sure that you're familiar with them. And we looked a little bit about finding paths, and in particular, if you want to find the shortest path, breadth first search is a good option. There are tons of other options, whole fields of computer science on finding paths. Come and join us in them sometime. But for now, breadth first search and depth first search will do just enough for you.